नमस्कार बच्चों, मेरा नाम धन्या और आज हम लोग ग्रेड 11 केमिस्ट्री का थर्ड लेसन स्टार्ट करने वाले हैं जिसका नाम है क्लासिफिकेशन ऑफ एलिमेंट्स एंड पीरियोडिसिटी इन प्रॉपर्टीज. ओके, so today we are going to learn about the history of periodic table, how we got the modern day periodic table, and also about some trends in the properties. Okay, now first of all, the question that came up was what was the need for the periodic table, or why was it necessary to classify the elements, or why was the periodic table so necessary? Okay, now in around 1800, only year 1800, only 31 elements were known. Okay, and as the year passed by 1865, 63 elements were already discovered. Now the number of elements discovered became almost double. Okay, so it became very difficult to study each element individually to find out their properties. So in order to ease out this problem, in order to solve this problem, the scientists searched for a systematic way to organize and classify the elements. So instead of studying the elements alone, they decided to group them into different groups and collectively study the groups, like organizing the elements in different, organizing the elements with similar properties in the same group and so on. Okay, now a lot of elements have been discovered, around 114 more and more are being discovered. Okay, so this was the necessity for the periodic table. Okay, and the periodic table that we have now is the work of a lot of scientists. Okay, now the scientist, okay, students, the scientist named Dobereiner, okay, this particular scientist observed a similarity in physical and chemical properties of several groups of 3 elements. Like he made groups of 3 elements, and he started studying and found out that the properties of these elements are same. Okay, so for example, if I have so the first scientist that we are going to learn about is Dobereiner, and he observed that, or he made a group of 3 elements and those properties who behave in a similar way, or whose properties match. So because they are taking 3 elements, that is why it is called as Dobereiner Triad. Triad means 3 elements. Okay, now for example, if I say take the 3 elements A, B, and C. Okay, now if I take the 3 elements A, B, and C, all these 3 elements behave in a similar way. That's why he grouped them in the as a triad. Okay, and also there was another observation made that the atomic weight of B, the one in the middle, okay, is equal to the mean of atomic weight of A plus atomic weight of C divided by 2. So the atomic weight of B is a mean of the atomic weight of A and C. For example, he gave an example of lithium, sodium, and potassium. So he's talking about, so this particular scientist is talking about the atomic weight okay, and he arranged them according to the atomic weight, okay, and as triad, okay, group of 3 elements. So the atomic weight of lithium is 7, this is 23, and potassium is 39. So let's check it, and they checked also 7 plus the 39 by 2. This comes to 46 by 2 is 23. So we got the answer for sodium, the element in the middle. Okay, this is one example. We took another example of calcium, strontium, another triad. This is another triad, barium. Calcium is 40, strontium is 88, and barium is 137. So calcium is 40 plus barium is 137 by 2. We are finding out for strontium. Okay, so this comes to 172 by 2, which is 88.5. So it is roughly, okay, almost similar to one that we have for strontium. So, okay, so this scientist, Dobereiner, suggested that the element that is there in the middle, for example, sodium or strontium, they have properties in between that of calcium and or rather, this particular scientist, Dobereiner, suggested that the elements that in the triad that are there in the middle had properties in between that of the other 2 elements. For example, strontium had properties in between that of 40 of calcium and barium 137. Okay. Similarly, sodium had properties in between that of lithium and potassium. Okay, now because they were arranged in groups of 3, it is called as triad and Dobereiner triad. Okay, so first time any scientist talked about the atomic weight and arranged the elements according to the atomic weight. Okay, now some of the successes of this triad was that the element who were grouped Okay, so some of the successes of this triad was that the elements who were grouped was based on atomic weight. Yes, so the grouping was based on atomic weight and the properties were similar. The properties were similar. That means the elements in the same triad had similar properties, similar chemical and physical properties. Okay, so first time any scientist arranged the elements according to the atomic weight. Okay, and the elements in the triad had similar properties. Now, what was the demerit? Why it was not followed for a long time, or what was the demerit? Okay, the demerit was that a lot of elements were discovered by then, so all the elements could not be accommodated. So all the elements could not be accommodated according to this law. Okay, so all the elements could not be, there was some discrepancy that was seen, could not be accommodated. So in the same triad, there were some elements that were not obeying this rule. So some discrepancies were seen. So that is why there was a need to modify this triad or this rule. Okay. So after that, so as I said, the modern day periodic table is a work of a lot of scientists. Okay. So this was the first scientist, Dobereiner, and the next scientist who worked on this was, there were many scientists. So the next scientist who worked on this was Newland. Okay, a scientist named Newland. And according to Newland gave the law of octaves. Octa means 8. Okay, now this particular scientist, Newland, he said that every 8th element had properties similar to the first element. Okay, so every 8th element had properties similar to the first element. For example, if I write lithium, beryllium, boron, calcium, nitrogen, oxygen, fluorine. Okay, noble gases were not discovered then. Okay, so sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium. Okay, so noble gases weren't discovered then. Okay, so if we take first element, the 8th element had properties similar to the first one. Okay, so if I am taking sodium, okay. So 1, 2, 3, 4, 5, 6, 7, 8. So potassium is the 8th element. So potassium will behave similar to sodium. Similarly, if I take the example of beryllium. So beryllium is first element, second, third, 4, 5, 6, 7, and 8. So beryllium will show similar behavior to magnesium. So this is the Newland's law of octaves, that every 8th element had properties similar to that of the first one. Okay. Now, also, this particular scientist arranged the elements in increasing order of their atomic weight. Okay. So, but this particular law, later on, they found out that it is true only for lighter elements. Lighter elements. So until calcium, it was fine. Okay. So until calcium, it was going fine. And also this scientist Newland, he talked about the periodicity. Now, what is periodicity? Periodicity. Periodicity. Periodicity means repetition of similar properties or gradual increase of physical and chemical properties after fixed intervals. Okay, so repetition of similar physical and chemical properties after regular intervals of time. Okay, so this scientist Newland gave the law of octaves, according to which the first element shows similar behavior or similar properties to the 8th element, and vice versa. Every 8th element has properties similar to that of the first one. Okay, and also this scientist talked about periodicity, that means gradual or repetition of properties, physical and chemical properties after regular intervals of time. And also, this scientist also arranged the elements according to the increasing atomic weight. Okay, Now, what are the successes? And one of the defects for this was that this was true only for lighter elements. Okay, until calcium, it was going fine. Okay, but the demerits of this law was when the noble gases were discovered. Okay, so suppose if the noble gases were discovered, then this seemed to be different then. For example, if I have lithium, beryllium, boron, calcium, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, etc. Okay. Now, if I take the example of sodium, this is the eighth element. Suppose if I take lithium, okay, 1, 2, 3, 4, 5, 6, 7, 8. Now it is not working, okay. So this was one of the demerits. So one of the demerits was that with the noble gas discovery, lithium started to behave if after the noble gas discovery, when we start to apply this rule, lithium will start, that means lithium will start behaving like neon. That is not true. So that means it was proved wrong. All right. So this was one of the demerits. So that means this rule was not followed could not be followed after the noble gas discovery. Could not be followed after the discovery of noble gases. This was proving wrong. Okay, so lithium will not behave like neon. Second demerit was that it could not be applied to heavier elements. Okay, so this was the demerit. So scientists kept on working on the periodic table, and the next scientist who gave the law was, or worked on the periodic table was Mendeleev. Okay, so he is also a very famous scientist. The next scientist was Mendeleev. Okay. Mendeleev, Mendelee, Mendeleev's periodic table. Okay, so another scientist, Mendeleev, worked on the periodic table. Okay, and this scientist gave the modern periodic law. Okay, Mendeleev also arranged the elements according to the atomic weight, and he gave the modern periodic law, which states that the physical and chemical properties of an element is a periodic function of its atomic weight. So that means Mendeleev also arranged the elements according to the atomic weight. He did not support that. He did not support octaves, but he suggested that the properties repeat after fixed intervals of time. So that means Mendeleev also supported periodicity. He did not support octaves, but then he suggested that the elements, the properties, the physical and chemical properties, repeat after a fixed intervals of time. Okay, and the meaning of a periodic function is depend upon. So that means the physical and chemical properties depends upon the atomic weight. Okay, so according to Mendeleev, 8 groups were now, according to Mendeleev, this is the Mendeleev periodic table. Okay, and according to the Mendeleev periodic table, there were 8 vertical groups. Okay, and there were 7 horizontal rows. Okay, Mendeleev also talked about valencies. Okay, in fact, he worked upon the formulas and talked about the valencies. Okay, and from left to right, we come across then we go from left to right, metal changes to non-metals. Okay, and one of the advantages was that until then 63 elements were discovered and all 63 elements could be accommodated in this periodic table. Okay, so he grouped the elements that had similar properties together. Okay, so lithium, sodium, potassium, okay, rubidium. So all those elements who had similar properties were grouped together. Okay, and all the elements were arranged according to their atomic masses. Okay, and also he left gaps in the periodic table. Okay, he left gaps for the undiscovered elements. Okay, so and also predicted the properties of the undiscovered elements. In your NCERT books, you have an information regarding under aluminium. Okay, below aluminium, he left a small gap. Okay, and named the elements as Eka aluminium and Eka silicon. Okay, and Mendeleev predicted gallium and germanium and described the properties, and later these elements were discovered. So he left some gaps in between the periodic table for the undiscovered elements also. Okay, so this was some of the merits or advantages of the Mendeleev's periodic table. But later there was some later, again, there was some discrepancies there also. And some of the demerits that was seen in Mendeleev's periodic table was some of the defects that was seen in the Mendeleev's periodic table was the first one was grouping of elements with dissimilar properties. Okay, so grouping of some elements with dissimilar properties were done. Dissimilar properties. For example, next to potassium, he placed copper. Next to rubidium, he placed silver. So that was totally dissimilar properties. Okay, then the next defect. So these were defect or demerits. The next demerit was like isotopes of hydrogen. Hydrogen had three isotopes having different atomic masses. They should have taken different position, but they were placed together. According to his rule, these because these hydrogen has different atomic number, isotopes of hydrogen have different atomic masses, they should have been placed separately, but they were placed in the same position. Okay. Some of these demerits made the scientists to work on the modern periodic table. And finally, with the discovery of noble gases were happening, and finally, there was a scientist called Henry Moseley. So you can see the modern day periodic table is a work of lot of scientists, all their ideas put together, and then it was a lot of changes took place according to the different observations. Okay, so this particular scientist, Henry Moseley, he observed that the frequency, the root of frequency of any element is directly proportional to the atomic number. Okay, so many scientists were doing research on different things. Okay, so the plot of root nu, that is the root of frequency over z, will be a straight line. Gives a straight line. Okay, so this showed that the atomic number z, the atomic number z is more fundamental property of an element. And so the Mendeleev's law was modified to get the modern periodic law. That means for every element, the atomic number is a more fundamental property that determines the property of an element. So the Mendeleev's law was changed and it became modern periodic law. According to this law, the physical and chemical properties of an element are periodic functions, that means depend on atomic number. Atomic number. So that means every element, for every element, the atomic number determines the properties. Okay, so there many scientists started working on the periodic table, and we got the long form of periodic table. Okay, that we have. Okay, and according to this, the long form of the periodic table, which had which had 7 periods, and there were 8 groups. Okay, these are the horizontal groups. Okay, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, and we also have the elements from 13, 14, 15, 16, 17, and 18 are called as P block element. I'll just explain what is P block element, okay, as we move on in the lesson. Okay, now if you see this particular element, La, lanthanide, AC, actinide. Okay, after this, you can see in some periodic table you have a gap, because this particular group of 14 elements of lanthanide should have been here, but because otherwise the periodic table will become very big. That is why they have placed it separately. But this is the position, lanthanide, this is the position, okay, for this whole 14 element lanthanide. Okay, this is the okay, so this whole of 14 element, this is the position. Okay, and for actinide, 14 actinide, this is the position. Okay, so 14 elements of lanthanide and 14 elements of actinide. Okay, these are called as F block element that you will be learning in grade 12. Okay, now this was the long form of periodic table. Many more elements are being discovered. Okay, now this periodic table. Okay, now coming to the some of the important features of the periodic table. Okay. Some important features of the periodic table. First of all, the blocks. What are these blocks? First is the S block element. Okay, S block element. Here, the valence electron means the last electron. Okay, valence shell means the last shell. Okay, the valence electron enters the S subshell or S orbital. Okay, and they belong to group 1 and group 2. So they belong to group 1 and group 2. Okay, for example, hydrogen. Hydrogen now it is kept separately, but for now, just explaining, if it has one electron, so it is 1s1. It is going to the first, it is going to the S subshell. So it is S block. Okay, now calcium. Calcium is 20, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. It is going to the S subshell. Okay, so here if I write for hydrogen, the valence shell is 1s. Okay, and for calcium, the valence shell means I said the last shell. It is 4s. Right? Now, this is the last shell. So valence shell, this is the last shell for hydrogen. That is the valence shell of hydrogen. Okay, now this last shell number will give you the period number. Period means this is the horizontal rows are called as periods. Okay, so this will give you the period number. So hydrogen is in the first period. What about calcium? Calcium is in the fourth period. So this valence shell number will give you the period number. Okay. Similarly, let's take one more example for sodium. Sodium is 11. So 1s2, 2s2, 2p6, 3s1. So what is the valence shell number for sodium? So this sodium is in period 3. Okay, and group number. These vertical rows are called as groups. So, group number, how to determine the group number? Group number is determined by the number of electrons in the valence shell. For example, sodium. How many electrons are there in the valence shell? 1. So, sodium belongs to group 1. This is group 1. This is group 2. What about the number of electrons for calcium? How many electrons are there in the valence shell of calcium? Or how many electrons are there in the last electron or the valence shell of calcium? 2. So calcium belongs to group 2. So this tells you about the group number. So shell number tells you about the period number. The number of valence electron tells you about the group number. So S block elements are from group 1 and 2. They are usually metals. They are called as alkali metals. And group 1 is called alkali metals. And group 2 is called alkaline earth metals. Okay. And they have a general electronic configuration of is NS1 to 2. It can be NS1, NS2, because why only 2 electrons? What is the maximum capacity for S electron? Is 2. So it can be 1 electron or 2 electron. And they are all metals. Okay. So this is the S block elements. The last electron or the valence electron goes to the S subshell. The next one is the P block elements. So the next one is P block elements. In P block elements, the valence electron or the last electron enters the P subshell. Okay. For example, if I take the example of boron, okay, it is 5. The atomic number is 5. 1s2, 2s2, 2p1. So, what is the period number here? This is the period number. So, it is in the second period. And the valence electron enters the p subshell. So, it belongs to p block element. Okay. Carbon 6. 1s2, 2s2, 2p6. It belongs, this also belongs to the second period. And because the last electron enters the p subshell, this is also called as p block element. Okay. And generally, from group 13 to 18. Okay. So I'll just share the screen. I'll show the periodic table once again. Okay. So here, students, group 13. So group 13 to group 18. 13, 14, 15, 16, 17, and 18. All of them, they are called as p block element because the valence electron or the last electron enters the p subshell. And they have some metals, non-metals more, and some metalloids here. Okay, so from 13 to 18 is the p block element. Okay, okay, students. Now I'll just show the general configuration of the p block element. So the last electron enters or valence electron enters the p subshell. Okay. Now the general configuration for p block element is ns2 np 1 to 6, because p subshell px, py, pz, what is the capacity? Capacity is 6 for the p subshell. Okay, so group 13 to 18, all these groups, we have the p block elements. Okay, so usually if you have some metals, more of non-metals, because it's on the right hand side. As you go towards the right, you have more of non-metals and some metalloids like gallium, germanium, silicon, etc. Okay, so this was about the p block elements. Now students, coming to the d block elements. Next one is d block elements. Valence electron enters the d subshell. Okay, taking an example of scandium. Okay, the atomic number is 21. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Last electron is the valence electron is entering the d subshell. Okay, so this has a configuration of ns2 n minus 1 d1. So if I generalize this configuration, ns2 n minus 1 d1, right? Coming to some element like chromium. Chromium is a special case, as we did the off-bow when we were doing the configuration thing. So here 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Is this what it should be, or what should come over here? Chromium is an exceptional case we discussed, because chromium has a half-filled d orbitals, because that makes it stable configuration. Okay, so this is a half-filled d orbital. Okay, anyways, it is filling the d orbital, so it's a d block element. Okay, now here the configuration, general configuration is ns1 n minus 1 d 5, general configuration. Right? Now, we have the general configuration can be written as ns1 to 2. Okay, so it can be either fully filled S or a half filled S like this. Okay, n minus 1 d. What is the capacity of d orbital? It is 10. So 1 to 10, because d has 1, 2, 3, 4, 5 of them. So 10 is the capacity maximum. Right? So it can vary from 1 to 10. Now, student, here, this NS subshell over here, this is called as ultimate shell, and the d orbital over here, it is called as penultimate shell. Okay, so this is the ultimate, the S subshell here is called the ultimate shell. Here in D, for D, it is called the penultimate shell. So in D block elements, the electrons enters the D orbital of the or D penultimate shell. Okay, and the D block elements are also called as transition elements. They are also called as transition elements. And all of them, they are metals and they behave as catalysts. They are very good catalysts, and also like nickel, cobalt, okay, or very good catalysts, and they form colored compounds. Okay, so these are some of the properties of D block elements. Okay, now students, just wanted to, because I mentioned transition elements, so just wanted to mention few things about transition elements. Okay, some informations about transition elements. Okay, now transition elements. Okay, now here the groups that are D block element are groups that are D block elements are group 3 to group 12. Okay, so group 3 to group 12, they are all transition metals. Okay, now for an element to be called as a transition element, they should have vacant d orbital. Okay, they should have a vacant d orbital. For example, scandium 3, 4, 5. Okay, they have vacant d orbitals. Okay, or chromium 1, 2, 3, 4, 5. They have vacant means at least they have space for more electrons to come in. So that's the they are referring to. That's the meaning of vacant they are here referring to here. Okay, but in case of zinc, that is 30, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. Here, there is no room for more electrons. It is fully filled. So although it's a d block elements, because the electrons are filling the d orbital, but the students here you can see for zinc, the electrons are filling the d orbital. That is why it is considered as a d block element, but it cannot be considered as a transition metal because it doesn't have vacant d orbitals. Okay, so the zinc is an exception. It's a d block element, yes, but it's not a transition metal. Okay, so all transition metals are d block elements, but all d block elements are not transition metal. So all transition metals are d block element. But so so scandium and chromium are transition metal. They are also d block element, but all d block are not transition metal. For example, zinc. Zinc is a d block element because the last electron is filling the d orbital, d subshell. But it cannot be considered as a transition metal because it doesn't have any vacant d orbital or a vacant or space for more electrons to come in. Okay, so vacant doesn't mean it's completely empty, nothing, not like that. A room for an extra electron. Okay, so that's why it is not considered as a transition metal, but it is considered as a d block element. Okay, so this d block elements, most of them, they are all metals. Okay, now coming to, first just let me show 3 to 12, group 3 to 12. So group 3 to 12. This part is called the transition metal. Okay, but this La and Ac, lanthanide and actinide, okay, and the 14 elements that follow them, they are called as F block elements that we will be discussing now, not in detail because you will be learning that in grade 12. Okay, so the F block element now, F block element, okay, that means the last electron enters the F subshell. Okay, now we have the lanthanide, the row full of lanthanide, 14 elements of lanthanides that follow the lanthanides, and the 14 elements that follow the actinide. Okay, now both of them, they are in group 3. Both the lanthanides and actinides, they come under group 3. Okay, and the configuration here, the lanthanides, for them, the last electron enters the 4f, and for actinides, the last electron enters the 5f subshell. Okay, now in these, the lanthanides and actinides, all of them, they are metals. Some are man-made, some are radioactive. Okay, and the configuration is found out according to experiments. Okay, so we can just memorize what is given. Okay, so for lanthanides, the general electronic configuration comes to, this is the 54, after 54, right? So 4f 1 to 14, 5d 0 to 1, and 6s2. Okay, so this is for lanthanides. Okay, and for actinides, it is Rn 5f 1 to 14, 6d 0 to 1, 7s 2, 1 to 2. Okay, so these are the general configuration of the lanthanides and actinides from the experiments. Okay, so these lanthanides and actinides are metals. Some of them, they are man-made. Some of them, they are radioactive elements too. Okay, so you can just memorize the general properties. Okay, now more about lanthanides and actinides you will be learning in grade 12. Okay, now coming to periodicity. Okay, now coming to periodicity. Now periodicity we already discussed in a bit before. It's the reoccurrence or repetition of similar properties after regular intervals of time when they are arranged in increasing order of their atomic numbers. So it is the reoccurrence. Writing the spelling wrong, sorry. It is the recurrence of similar properties of an element after regular intervals of time. When the elements are arranged in increasing order of atomic number. So now we are going according to increasing order of atomic number. Now, what is the cause of the periodicity? For example, if I take lithium, sodium, potassium, okay, and so on. Okay, as we are coming down, there is repetition of properties, okay, or the radius is gradually increasing, or the ionization is the ionization potential, as you're coming down, the ionization potential is gradually decreasing. Okay, what is ionization potential and all we will be discussing. Don't worry about it. For now, there is a gradual recurrence of the properties. Okay, so it's like changes only. They are behaving in a similar way. They show similar chemical and physical properties. Now, what is the cause of this? Okay, now here, for example, lithium, the configuration is 1s2, 2s1. This is 1s2, 2s2, 2p6, 3s1. This is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Okay, now all of them have how many electrons in the outermost shell? 1 electron in the outermost shell. So, students, the periodicity, or why they are all behaving in a similar way, because they all have same number of electrons in the valence shell. I already told you valence shell is the last electron where the electron enters. Okay, in this case it is 2s, so that's the valence shell. In this case it is 3s. In sodium it is 3s, that's the valence shell. In potassium it is 4s, that is the valence shell. Okay, so the periodicity, or why the elements are behaving in the similar way, is because of the same number of electrons in the outermost shell, or the valence shell. Okay, now similarly, there is something called diagonal relationship. Okay, many more properties will be discussed. So as we move on in the lesson, okay, so just general topics, just I'm discussing now. Okay, because all these properties are very important too. Then I have something called diagonal relationship. Diagonal relationship. Okay, just go, the same meaning, it has diagonal. Okay, so lithium, beryllium, boron, carbon. So I'm taking sodium, magnesium, this is the next period. Okay, aluminium, silicon. Okay, now over here it is seen that elements in different periods show diagonal relationship. For example, lithium shows similar behavior like magnesium, beryllium shows similar behavior like aluminium, boron shows similar behavior like silicon. It's like diagonal. Okay, so this is called as diagonal relationship. So the striking similarity between the first element of the group and the second element of the adjacent group. Okay, so this is the first element. This is the first element of the group and the adjacent element of the next group. Okay, on the right hand side. And this is called as diagonal behavior. Okay, why this happens? This is because of same charge to size ratio. That means the charge to size ratio of lithium is similar to that of magnesium. Beryllium is similar to that of aluminium. That is why, because of similar charge to size ratio, which is also called as charge density, they show this diagonal relationship. Okay, and it is also called as polarizing power. Okay, so this is called as diagonal relationship. So the similarity between the first element of a group with the second element, this is magnesium, is the second element of the adjacent group towards the right hand side. It is called diagonal relationship, and this happens because of the charge to size ratio, or we can also call as charge density. Okay, students. So today we discussed a bit about the history of how we got the modern periodic table and some properties in the periodic table. Okay, more about the periodic table and the different elements we will learn in our next video. Okay, so that's all for today, students. Thank you. Have a nice day.